All right, so for the next topic, which is cross sections, finding volume of a solid, but in this case by defining this volume in terms of a cross section. So what is a cross section ultimately? Well, so suppose, well, again, we're setting up the integral between the square root of x and y equals x squared, all right? To keep a very simple region. Of course, what we did in the first part of this section is to rotate about, well, the x-axis or the y-axis. And now, when we rotate that, the way we derived the formula to find the volume was by not by finding the area of a rectangle, but rather that rectangle, when rotated, gave rise to a mini cylinder, right, or a disc. So that's why we call it the disc method. However, in this case, how about not rotating, but rather instead chopping this region of integration, instead of rotating, having squares. All right, we need a 3D perspective over here so you can see what I'm talking about. And in this case, well, we can choose to create squares. Okay, so I want to fill this region, so the entire region, with n equals 1, n equals 10, n equals 12, 22, okay, just a few. And see how the region looks like. If we look at from the side, we have cross sections that are square. All right, so but how do we find the volume? Well, we'll see. So this is what we would see in our paper in 2D. However, you can think of these squares right here as popping out of the your paper. All right, and that's the volume that we will define. Okay, another possibility is to have equilateral triangles, and well, you can think of equilateral triangles popping out of their paper as well. All right, so that's how it would look like in 2 dimensions by drawing it, but giving it some perspective, it would look like this in the cross-section point of view. All right, the other possibility is having semicircles. And well, this looks sort of the rotation about the x-axis or the y-axis because of the circular shape. However, in this case, this region is not being rotated. What we're doing is putting circles in this case. All right, and again, from the 2D perspective, it's going to look like this, and circles, or rather semicircles, popping out of the paper. All right, now this is, you can think of this like the generalized way to get to the, to the disc method, but again, in this case, as opposed to the disc method, the region remains static. It doesn't get rotated about any axis like in these cross sectionals. All right, so how do we set up the integral? Well, so what happens here when we have, so they're going to tell us how in this case what the shapes of these cross sectionals are going to be like. Are going to be squares, equilateral triangles, or semicircles. And again, the same thing about top minus bottom, it's going to be here because, okay, let me go back to the animation here. So when we have squares, so you see these square cross sections, but well, every single square will have a different dimension based on the distance between the two functions, right? So that is, this square right here is smaller than the square right there due to the distance between those two functions, right? And well, how do we define that volume? Well, recall that in general the volume is found by multiplying the area times the length. So that's why what we're going to do is add every single area, putting them together, and come up with the volumes. All right. So, and in this case, well, the formula to find the area of a square is only the length of the side quantity squared. But that length of the side, okay, coming back to the picture, wouldn't that be okay, something's going on, hold on. Okay, I can't hold it. Wouldn't that be actually the difference or the distance between the two functions? That's the length of the square. And for the equilateral triangle, well, that's a formula that we don't use very often. Typically we use right triangles, but in this case, equilateral triangle, that's the square root of 3/4 times the length of the side square, and also that length of the side when having equilateral triangles. Okay, I can't move it. Anyway, well, these lines right here are actually the length of those triangles. And same for the semicircle. Be careful, because for the semicircle we would be talking about for the area of the circle. That's always the pi times the radius squared, right? But in this case, these lines right here are not defining the radius of that semicircle. What are they defining otherwise? The diameter. So in order to get the radius, what do? Divide by 2, right? So that's why I have top minus bottom, which represents the diameter of that semicircle, but dividing it by 2, that's going to be the radius squared. And 1/2, well, that's because it's the semicircle in this case. It's not the whole circle. Otherwise, if they were circular cross sections, well, we wouldn't multiply by 1/2. All right, and well, the volume is obtained by adding this, by finding the integral of the formula that we set for each region and within the limit. All right. Okay, and by the way, notice from the animation, okay, hopefully I can, got it. Okay, notice how these cross sections are perpendicular to the x-axis, they're parallel to the y-axis, but they're perpendicular to the x-axis, and actually it's going to be there in the wording of the problem. So this they're perpendicular to the variable with respect we're integrating. So let's look at one example. The base of a solid is bounded by y equals e to the x, the y-axis, and x equals to 4. So let's graph. And okay, the graph of e to the x, which is an increasing function like this, it has a y-intercept at 1, and the y-axis is one of the bounds, and x equals to 4. All right, 1, 2, 3, and 4. Okay, what's the picture here? We have cross sections that are squares perpendicular to the x-axis, and well, hopefully you can see the picture here. You can think of, in this case, squares popping out of your paper, which is what I will try to draw here with some perspective. There's one, that's another square. All right. If we had our eye in this direction, we would see the squares in the same way that we did in the animation. Are you following me here with this picture? I know it's kind of trying to do a 3D picture. It's not easy to do, but hopefully you can follow me here. Well, so in this case, we need to set up the area function that we will integrate. That is a of x equals, well, because in this case we have squares as cross section. What's the area of the square again? The length of the side square, right? That is s squared. But those lengths, so this length right here, the length of the square, which is this length, it's also this length. Isn't that the top minus bottom? All right. So, okay, but in this case, what's the top? What's the bottom? So the top is the exponential e to the 2x, and the bottom is 0, but this is simply e to the 2x quantity squared. And is that equal to e to the 4x squared? What's the answer of squaring e to the 2x? Does that look right? Anyone? 4x, right? Power of another power. We multiply 2x times 2, which is 4x. Okay, so we have a function to integrate in this case. So the volume will be the integral. The limits of integration in this case, they're given. It's going to go from 0 to 4, and that's a of x with respect x, and this is the integral from 0 to 4 of e to the 4x with respect x. And well, the integral of e to the 4x is itself e to the 4x times 1/4, and evaluated from 0 to 4. All right. And well, using the fundamental theorem of calculus, this is e to the 4 times 4 minus e to the 4 times 0, and this is 1/4 e to the 16 minus 1, because e to the 4 times 0, which is e to the 0, e to the 0 is 1. Any number to the 0 is 1. And we can leave this as a final answer. All right. Sure, we have some time for do one more example. Maybe at least set it up. So what do we have? The base of a solid bounded by y equals to 2x and y equals x squared. Well, so I'd rather use the same region over and over. That way we don't have to spend too much time finding points of intersection. So that's 2x and squared, and the points of intersection 0, 0 and 2, 4. Now in this case we want to find the volume having cross sections to be semicircles in this case. All right, so we can think of semicircles popping out of over paper like this, just like in the animation. And again, if we put this into perspective and we were viewing the region in this direction, we would see those cross sections as semicircles. But now recall that in this case, to set up the integral right here, we need the a of x. A of x for semicircles. Number one, because it's a semicircle, we need to have 1/2 of the area of the circle, and that's pi r squared. All right. But r, in this case, well, in this case, the r, recall that this distance between top minus bottom, which is not the radius, it's rather the diameter. So for this reason, that's the top minus bottom. But in this case we divide by 2 in order to have a radius. Otherwise, well, it would be, and from here this is 1/2 pi top. In this case, which function is the top? Is it the line or the parabola? The line, 2x, minus the bottom, which is the parabola, over 2. And well, let's simplify this a little bit. Squared. This is then 1/2 pi 2x 2x minus x squared, quantity squared, over 2 squared, which is 4, and then we can multiply this 1/2 times 4. That's 1/8 pi 2x minus x squared, quantity squared. And well, when setting up the integral, volume equals integral from a to b of a of x with respect x, and that's the integral from 0 to 2, because we want limits of integration in the x direction, and that's a of x, the formula that we already found out, 1/8 pi, and that's 2x minus x squared, quantity squared. And for the sake of time, I'll give you the result of this integral. This should give us 2 pi over 15. All right. Now let's just justify very briefly this formula. Well, we're essentially multiplying the area times some length. Isn't that going to give us a volume? And then integrating, that's basically adding infinitely many of those volumes. So that's why this result should give